Hi, in this video, I'm going to show how to use the Laplace transform method to solve this initial value problem. You may notice that you could solve this initial value problem using other methods, such as undetermined coefficients or power series. Of course, but I'll show you how to use the Laplace transform, and you may find out that Laplace transform is the easiest way of solving this if you're good at algebra. To apply Laplace transform to solve initial value problems, you need a good table of Laplace transform that has two things in it. A typical Laplace transform table looks something like this. There are two parts to this table. The first part contains properties of the Laplace transforms, how the Laplace transform behaves when applied to different kinds of functions of t. And then the second part, given a function in t, what is its Laplace transform as a function of s? So all that is part of the second part. The first part is properties of Laplace transform. Second part, Laplace transform of specific functions. Most people do not have second part memorized. This is unlike when you learned derivatives and integrals in calculus, where you're supposed to memorize the entire table of derivatives and the entire table of integrals. Most people don't expect you to have the entire table of Laplace transforms memorized. As you use them, you will end up memorizing a few of them, but probably not all of them. The properties of the Laplace in the first part of this table often do not show up in many Laplace transform tables, and they are the things you're supposed to know and memorize and got committed to memory. The good news is, in a typical class, you won't be dumped with all of these properties all at once. Chances are you'll be learning a few properties at a time. And so eventually you'll get them all anyway. Some of the important properties include, for example, this one, which says that the Laplace transform is linear. You start out with a linear combination of two functions. You arrive at the linear combination of the transforms. The second property that you should really know very soon is how to take the Laplace transform of derivatives, because that is how you transform a differential equation. You have to have all the transforms of the derivatives. And the third thing you probably know almost right away, actually these two, these are Laplace transform of a shift in S or a shift in T. And then, of course, there are a whole bunch of others, the convolution rule, etc., etc. But right now, I'll show you how to memorize the formula for the derivatives. Let's say you have the nth derivative of function y of t. Traditionally, whatever function you have, f, y, x of t, in the original equation, we would write the capital letter of that letter. The Laplace transform of little f would be capital F of the variable s. The Laplace transform of y is capital Y in S. And the Laplace transform of little x is capital X in S. That's the convention. So you have the nth derivative of y in t, and you want to take the Laplace transform of it, then this is what you do. First, you write down s to the power n, which is the same power as the derivative, times the Laplace transform, so times y. That's your first term. Everything else is a subtraction after that. So you have many minuses after that, where the power of s starts going down, Sn minus 1, all the way down to Sn 1. And each of these is multiplied by the initial value of the function. So the initial value of y and the derivative of it goes up. So the power of s goes down, the derivative of y goes up. So y prime at 0, y double prime at 0, all the way down here, it would be y to the n minus second derivative and y to the n minus first derivative at 0. And you'll never get to y to the nth derivative at 0 because in an initial value problem, you're given the initial value up to the n minus first derivative only. So that's how you write the Laplace transform of a derivative. Power of s goes down, the derivative y goes up. The very first one is s to the n times y plus everything else is a minus. Right, that's how I remember it. All right, now let's get back to solving this initial value problem. In solving Laplace transform, you basically have 3 steps, except that step 3 is kind of hard and long, so I think of it as 4 steps. Step 1 is to take Laplace transform both sides. So you go from the xt universe, you take Laplace transform, you get to the capital X of S universe. And then step 2 is you solve for X. In some situations, this solving step involves algebra, no calculus whatsoever. In some other situations, you may have to solve a differential equation, but it will be of a lower order than the equation you started with. And then in step 3 and 4, you do the inverse. So when you do the inverse of Laplace, you get back to your solution. So this is a little x equation, which converts into a big X equation. And you get your big X solution, which you convert back into a little x solution. So those are the 3 steps. The third step can be complicated. So in this solution, I'll break it into 2 steps. And I want you to think of it as 3 steps, though, whether a third and fourth step are the same one. Let's now go for it. Step number 1 is to take Laplace transform both sides. On the left, you have, or this is equal to the Laplace transform of the right. All right, on the right-hand side, let's look up the Laplace table. There's a formula for Laplace of e to the ax. Here, a is equal to -1. So on this side, it is 1 over s minus -1, which is s plus 1. On the left-hand side, that's a linear combination, so I can break it up. The Laplace transform of little x, that's just big X. Laplace transform of x prime. So now I use what I know of Laplace of derivative. First, I have s to the first times capital X, and then everything else is minus. Well, the power of s goes down, so from s it goes down to 1, and the initial values go up. So I'm done. This one is a little more involved. I start with s squared x, and then everything else is a minus, where the powers of s goes down, so minus s minus 1, and the initial values go up, starting at x of 0 and then x prime of 0. I look at the question and all of these are equal to 0. So now the combination is s squared x plus 4sx plus 8 capital X is equal to 1 over s plus 1. Then with step 1. Step 2, solve for x. This is a linear equation in x. I can factor out the x. And therefore, x is equal to. All right, in differential equations, just like in calculus, when you have things that are factored, you can leave them as is, unless you have a compelling reason to multiply them out, otherwise don't. All right, step 3 and 4 combined together is to take the inverse Laplace of x. But if you look at the table of Laplace transforms, you don't see anything that looks like the expression that we have. Nothing in this table looks like it. So that's why I break up the third step into 2. Step 3 is to break or rewrite as a linear combination of things that do appear in the Laplace table. And maybe a simpler way of thinking of linear combination is as a sum of. All right, let's go back to the table. This is s plus 1. S squared plus 4s plus 8 cannot factor because it doesn't have any real zero. You can see that b squared minus 4ac, b squared is 4 times 4, minus 4ac is 4 times 8, so it's a negative number, doesn't have a zero. And I don't have any Laplace transform that look like this in the denominator, but I can see that some of them looks like parts of it. This s plus 1 in the denominator looks like s minus a here. And then this s squared plus 4s plus 8. If you have a quadratic that does not have a zero and does not factor, then it's like a parabola that's completely above the x-axis, or in this case, the s-axis. Well, that means it's some sort of square plus a number, right? That's why you don't have a zero. Once I start thinking like that, then I say, hey, so maybe I should write it as some kind of square plus a number. That's completing the square for you. This is s squared plus 4s plus 4 plus another 4, where this is my completing the square, s plus 2 quantity squared. That's this, except that it's s plus 2 instead of s. That's a phase shift, and a phase shift in s corresponds to a multiplication by e to the at in the t universe. And sure enough, it's down here in the table. So I have a capital X that has a product in the denominator. If I can only separate them into a sum of each separate one, then I could have one of it is the e to the at, that's the s plus 1 denominator, and the other is the s plus 2 squared plus 4. That'll be some sort of like e to the at cosine or e to the at sine. Well, the technique of separating a combined denominator into two separate fractions is called partial fraction. Right? So yeah, I guess that's what I'm gonna do. Partial fractions separate out an s plus 1 and an s squared plus 4s plus 8. The numerator for the s plus 1 is a constant. The numerator for a quadratic that's not factorable is a linear expression, so it's some kind of bx plus c. Common denominator. And in the numerator, I have as squared plus all this. And now I combine like terms, all the s squares. Oh, these should be s's. All the s's and all the constants. And all this should be equal to 1 over that same denominator. All right. So back here, if I set s equals to -1, I'm only looking at the numerator. Then this second term is gone. And in front, I have 1 is equal to a times 1 minus 4 plus 8. And that's 5. So a is equal to 1/5. Whereas down here, if I set this whole thing is equal to 1 over the same denominator, then I have a plus b is 0. The s squared term is 0. The s term is also 0. And the constant term is equal to 1. Well, I already know a is equal to 1/5. So this one gets me b is equal to -1/5. And this is 8/5 plus c is equal to 1. So that gets me c is equal to 1 minus 8/5. C is equal to -3/5. So my partial fraction is that x is equal to the s plus 1 term comes with a, so that's 1/5. The s squared plus 4s plus 8 term comes with bx plus c, bs plus c. I keep calling it x. And in order to use the formula from the Laplace table, I'm going to rewrite this as before as s squared plus 4s plus 4 plus 4. So it's s plus 2 squared plus 4. Might as well write 2 squared. And matter of fact, I'm going to separate it out because there is the cosine formula with an s and the sine formula without an s with just a constant. So minus 1/5 minus 1/5 here plus -3/5 over. I'm almost there. This is the e. This is the cosine, and this is the sine. But the cosine, if I have s plus 2 in the denominator here, then I also need s plus 2 in the numerator. So it'll have to be, I have to put in an extra 2. And since I put in an extra 2, I have to take it out. Plus 2 minus 2. All right, minus 2 times -1/5 is plus 2/5 minus 3/5 divided by 2/5 minus 2/5 is -1/5. Almost there. The last thing is, if I want to use the sine formula, this k here needs to appear up on top. So I need a 2 on top. So I'm going to multiply by 2 and divide by 2. Finally, I'm ready. X is equal to, this part is going to be an e to -at. This part is going to be a cosine. And this is going to be a sine. Step 4, inverse Laplace. I take inverse Laplace, and I get little x of t. That plus 1 becomes -t is x is s minus a -1. This one becomes e to the -2t cosine 2t. I want you to notice that the two number 2's come from 2 different places. This one gets you that -2 there. And this gets you that 2t there. Okay. They're the same value of 2, but they come from 2 different places. And finally, minus 1/10 sine of 2t. And there we go. That's the answer. All right, so let's summarize the steps. Step 1 is to take Laplace transform both sides. And that way, an equation in little x of t becomes an equation in big X of s. Step 2, you solve that equation for big X of s. Step 3 and 4 are to take the inverse Laplace of big X to become little x. But let's do it in 2 steps. So to rewrite the solution big X as a linear combination of, or sum of, think of it as a sum of, and then with an extra constant coefficient in front, of terms that appear in the Laplace table. Once you have that, then you can take the inverse Laplace. And you arrive at the solution little x of t. All right, that's it. Any questions or comments, put it in the comment section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.